Assalamualaikum to Dr. Aizan and my fellow friend. Okay, for this group project, our group gonna present about the design and simulation of closed loop control system for screw oil press. Our group consists of 5 people: Muhammad Arifan, Muhammad Azri, Muhammad Zulhairi, Luqman Hakim, and myself, Muhammad Ibn Zahari. Okay, our content, we will start with the introduction, problem statement, application, and block diagram of closed loop system with result and discussion, and we will gonna close with a conclusion. Okay, we will go to the introduction first.
So let's begin the presentation. For the introduction, nowadays the demand for edible cooking oil has increased dramatically. The screw oil press is the most common type of mechanical crushing equipment. So when the screw press is operating in the press oil procedure, it is essential to understand the actuation sequence and control process in order to avoid energy waste caused by the operation of workers. Next is the problem statement. So several disadvantages of the traditional screw press exist, including a lower level of automation, an unstable control system, and a longer time to respond than modern screw presses. So a set of automatic closed-loop control system for the screw press has been developed as a result of research into the principle of pressed oil, the mechanical structure, and the automatic control procedure of the screw press. So the control system is based on programmable logic controller PLC, control and the proportion, integration, differentiation, PID control strategy. Next is the application. So based on the analysis, a set of closed loop control system for the screw press based on a programmable logic controller is provided. So the configuration consists of PLC controller, an inverter, a feeding control system, a pressure sensor, an AD module, and others component. So that's all from me.
Now we will go to the block diagram of a closed loop system. As you can see here, this is a picture of a basic closed loop system which has input, error detector, controller, plant, and feedback element. Okay. The error detector receives the input. The input is sent for changing the input form according to the nature of the controller. The controller receives the signal from the error detector. The controller will generate a control signal based on the applied input signal. The system conducts the appropriate action and produces a certain output based on the generated signal, where a portion of signal is returned to the input to check whether the generated output matches for our desired output. This is the indicator of a feedback, where an error signal is formed when this feedback signal is compared to the reference input signal. The controller receives this error signal, where the controller then generates an altered control signal, which instructs the process to correct the error in its output. As a result, at the end of the operation, the required output is tail. From our journal, we get the block diagram as shown below, which is industrial personal computer, PID controller, pressure changer, AC motor, feed motor, screw feeder, pressure sensor, and AD module. Now we go to the mathematical model. Okay, for your information, mathematical model is a set of mathematical equations that used to describe control system. This model are used for control system analysis and design. Having the input and mathematical model for control system, finding the output of the system is possible, where after the input and output is known, the control system can be designed by discovering the mathematical model. In this case, by unit feedback, the control method utilizes a continuous control method, where system control process are shown as the next slide. Okay, this is our mathematical model, which is our input RS, and we will go to the ES, DS, US, and we will produce a GS in the output. We have the DS equal to KP plus KI and KD, where KP is a proportional coefficient, KI is integral coefficient, and KD is differential coefficient. For our screw press transfer function, we get as gs equal to 5 over s squared plus 3s plus t. And next, I will pass to my friend to present.
Now, I will present the analysis of the results, including the discussion for each of the results. So based on the figure shown here, the perfect data from the journal shows the gain for the system have a good control effect, fast response speed, and no overshoot. So this is the optimal value for the journal to eliminate the dynamic error, overshoot, and steady state error. However, the effect of each controller contained in the PID controller can be observed by the changing of parameter of the components involved. So first, for our project, we are changing the parameters of KP, which is the proportion parameters, and the value is changed from 0.05 to 0.5. The system response are increased by achieving 0.5135 in 2.217 seconds, while the normal condition achieved the value of 0.5065 in 4.065 seconds. So the increase of response time benefits the system on giving the output as the system receives the input. Even though increasing the value of response time may be beneficial, the excessive increase of response time may cause the system to overshoot and cause the steady state error. So based on figure below, the value of KP is 1 and shown indicate the system is overshoot. This is why the system cannot have the value of proportion parameters excessive amount. So next I will pass the presentation to Zulhairi. Thank you.
Hello and Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Zahiri and I will explain about the changing the parameter of Ki, which is integral coefficient. The first integral coefficient change into 0 from 0.05, and this is the graph of the Ki equal to 0, and the percent overshoot obtained is 0.505%, and the peak to peak is decreasing from 0.998 into 0.07758. And then if we change Ki into the 0.75, the percent overshoot obtained is 34.46%, and peak to peak is now obtained 1.34. This is because the integral coefficient in PID control how much the control output is produced due to the accumulated position error, and by adjusting the coefficient, the integral coefficient, the steady state error may be eliminated, but may make the transient response worse if not adjusted properly. Okay, that's all from me. Thank you. I will pass to the next presenter.
Assalamualaikum. My name is Muhammad Azri bin Muhammad Azib and my metric number is 201054. I will be presenting on the changing the parameter of KD. So for our new parameter, KP is equal to 0.05, KI equal to 0, and KD is equal to 0.9. So this graph shows the system response of our system. Okay, so what happened when the parameter of KD is changed? So the system response starts to overshoot. The percent of overshoot of the system response is 5.851%. For the system to be stable, the resist time must be reduced so that the speed of response may be enhanced, as well as the maximum peak overshoot. The time rest is defined as the time for the output waveform to increase from 0.1 to 0.9 of its final value, which is 6.503 seconds. The KD in the PID controller is used to implement derivative action. Derivatives were formed in response to the rate of change in error. So, our conclusion, some typical working conditions in batch production for the screw press are discussed in this report. The control systems completed design and simulation are carried out using the reset instruction sequence control system, design method, and simulating toolbox. Using simulation experiments, it has been demonstrated that the design of the closed-loop automatic control system can increase the level of automation in screw press operation. It is not possible to ensure accurate control parameters because the PID controller's parameters are obtained using a single variable testing method. So that's all from us. Thank you.